I will present today shared work with one of my students, Jin Xu, and my colleague Mariët Theune about leveraging annotator disagreement for text classification. So, sorry, let me. Usually, when we think about text classification, what we do is when we build a corpus for text classification, what we usually do is we take when we have multiple annotators, we try to get rid of disagreement between annotators, for example, through majority vote. So we take 5 annotations, for example, and then take whatever the majority voted on as ground truth in our data set. And very often also inter-annotator agreement is used as a measurement for data set quality. So if we have a high agreement between annotators, often we say that the annotation in the data set is reliable. So that's what was the standard for a long time, but recently there has been a push towards questioning these practices and embracing disagreement between annotators. Because if 3 annotators say A and 2 annotators say B, then potentially there is some valuable information in this disagreement, which should not just be thrown away, but should actually be considered in the training process, for example. And that is particularly, but not only true for tasks that are more subjective, like, for example, hate speech detection, where we know from the research that whether a certain post is classified as hate speech or not strongly depends on the background of the person annotating it. And an increasing number of data sets that are published now actually contain unaggregated labels. So not just this majority vote anymore, but we can actually see the individual annotations. And we looked in this paper at different techniques, how we can leverage these unaggregated labels. So how can we use them to make better predictions? And for that, we particularly used 2 data sets. The first one is the large-scale hate speech data set by Theune et al. It contains 100,000 tweets, and each tweet in the data set is annotated by 5 annotators that have been selected randomly from a panel of 20 annotators. That means we have 5 annotations per tweet, but it's not always the same 5 annotators. And the labels that can be applied to one tweet can be hate, offensive, or normal. The second data set that we used was abuse in conversational AI. And that's a data set that consists of conversation between users and a conversational AI systems. And we have 2,500 training samples in there and around 1,600 validation and test samples. And there we have a bit more fine-grained labeling. We have not abusive, we have ambiguous, we have mildly abusive, we have strongly abusive, and very strongly abusive. And we compared 4 different methodologies to use these labels as a baseline model. We fine-tuned a BERT model in the traditional way, meaning we aggregated the labels through majority voting and then took that majority vote as training. Then the second approach that we tested was a probability-based multi-label method. So instead of predicting just the most likely label, here we try to predict a probability distribution for all existing labels, so that a tweet is not, for example, just classified as hate, but like in this example, we have 60% hate, 20% offensive, and 20% normal. And for that, we use the probability distributions from the unaggregated labels. Then the third approach that we compared was an ensemble system, where we trained a separate BERT model for each set of labels and later then aggregated these results. So again, as I mentioned, it's not always the same 5 annotators, but if we have 5 annotators for every tweet, then we have 5 BERT models, which we train with this unaggregated information, and then in the end combine that for the prediction. And lastly, we used instruction tuning. So we used Llama 2 and then instructed it with examples to behave either very critically, like the most critical annotator, or less critical annotators, and then again got multiple predictions that we combined to a final prediction. And well, evaluating a system that is not based on a single ground truth is actually not that trivial, because the question is, if we don't assume anymore that there is something like a ground truth, a gold standard, then what do we compare against actually? And one possibility that we also used is to use cross entropy. Cross entropy can be used to measure or to compare two different probability distributions and see how close they are to each other. And what we want to achieve here is we want that our prediction has a distribution that is as closely as possible to the original distribution, so that we kind of represent all the opinions that also have been in the initial data set. And here a lower score means better. So the lower the score is, the closer our prediction is actually to the original distribution. And you can see here on the left, that is from the hate speech data set. And you can see that the multi-label approach, where we predicted the probability distribution, actually performed best. For both the ensemble system and the instruction tuning, we compared different approaches. So top 5 means that we used all predictions. So we had a model for all 5 annotators and we took all of them, whereas top 4 and top 3 means that we only took the 4 or 3 models which had the highest certainty in their prediction. And as you can see, the smaller the number of models that we used is, the better the predicted distribution fitted the original distribution. For the other data set, for the abusive conversation data set, that is much more fine-grained, and we actually see the opposite. So here the multi-label approach was not performing so well, and for the ensemble system and the instruction tuning, actually the more of the submodels we integrated, the better the prediction got. Again, probably being the case because here we have a much more fine-grained labeling. And we didn't just use this cross entropy to evaluate, but we also conducted an online survey where we asked participants which prediction they actually thought to be more representative. So we showed them our baseline model, which only put out, for example, hate speech for one tweet. And then we showed them the different, the multi-label model, where they get a probability distribution instead of just this one value. And then we asked them which of the versions they think is a better representation of the tweet and a better representation of whether it contains hate speech or not. And what we actually found is that the majority of participants preferred the multi-label approach, in which they got a probability distribution and not just the most likely value as response. Also, some of them said for them it didn't make a difference, but the majority preferred the multi-label model, which had multiple outputs also. To conclude, the work showed that using and predicting unaggregated labels is actually perceived as a better representation by users compared to just aggregating labels. That's at least true for the task of hate speech detection that we were looking at. But there's also for some other tasks already some research done which suggests the same thing. So it is really a good idea to consider the original unaggregated labels instead of just the aggregated ones. And performance-wise, we saw that which approach performs best strongly depends on the underlying data and features like classification difficulty, the total amount of data that is available, the number of labels that is available, but also the number of annotators per item. With that, I want to conclude. Thank you very much for your attention. Are there any questions?